I add some additional things to this topic. So
Nice. That's good you asked.
yeah.
One second.
All right. Hi, everyone. Thank you for being here. We're happy to start the seminars for this semester by having Professor Zhong here. He's the associate professor here in Mechanical Engineering Department at WPI. He has received his PhD from Penn State University at 2005. And for a short time, he has been working as a research associate. And after that, he has joined Saint-Gobain High Performance Material Research Center in Northborough, Mass. And he worked there as an internal technician consultant. He's been applying thermodynamics and kinetic to various R&D projects there. And after that, in 2013, he joined Florida International University as an assistant professor. And at 2017, he joined WPI as an associate professor. So some of his awards are, he has been awarded the TMS FMD Young Leader Professional Development Award in 2016. He's also been awarded the ONR Summer Faculty Fellowship in years 2015, 16, and 17. He has 66 peer-reviewed journal papers, 2 book chapters, and 2 patents. And his talk today would be on the novel hybrid modeling for the design of aluminum, cobalt, chrome, nickel, iron, high entropy alloys. It's a pleasure to have you, and the floor is yours.
Okay. All right. Okay. Yeah. Thank you for the introduction. Okay. Let me see. How do I? Okay. Hi everyone. So looks like this is like the first seminar in the C term. So it's my great pleasure to give you an idea what we have done in the last 2 or 3 years. So as introduced, this is about the high entropy alloy, and let me see. And we want to talk about our novel hybrid modeling, right? So there are some like results, just giving you some idea, right? Like what we have done. Okay, and here listed the photo of me and also the students actually get involved in this project, and some of the students actually are sitting in the classroom, right? Okay, so after my talk, if you have questions, you can contact with me. You can also contact with my students for the details. All right, so I prepared these slides half a month ago, and I already, gave this talk externally a couple of times, right? And those are like this very long talk. So I have slides to cover probably 1 hour or a little bit more, right? So, but today, because the limit of the time, right, I want to greatly shorten the content that actually I will cover. So I will only talk about the main contributions we have instead of talking about like the details step by step, how we work on this. All right. Okay. So that's one change, right? And the second change is when I prepare this slide, right, I just realized one thing, right? So besides this technical contents, right? So technology-wise, there are actually quite a lot of progress, right? So especially, right? So this is just the beginning of 2023, right? So I want all of you actually go to this, right? Go to this. Let me see. Oh, it does not show here. Let me see. How do I do this? Hold on. It didn't show. Do I have a post somewhere? No, not here. Where's my app? Okay. So here, right? Okay. So please, yeah, it's still here, right? So please log in, right? I think probably most of students are familiar with this Poll Everywhere, this software. So when I say recently, right, I'm talking about like, for example, in 2022, right? So what would be your view of this news or breakthrough in technology, right? Try to limit your answer to 1 or 2 words, right? I don't know for the students with Zoom, I don't know if they probably can add their inputs as well, right? Okay. Oh. Yeah, looks like. Is this actually working? It will appear here, right? Okay, so let's give a minute or so. Oh, all right. Okay, that's good. Okay, so probably, right, that's most of the answers. So I think this is a good way to summarize, right? So what a human being actually achieved in last year, right? So fusion, of course, right? Additive manufacturing, quantum, computing, right? Advanced energy, right? Some novel alloys, I guess, right? And this computing and battery, of course, right? So everyone probably hear about a lot of news on battery as well. So and in the middle, right? So we have this Chat GPT. So personally, I also vote for this Chat GPT. I think
Why don't you eat lunch?
right, a lot of students actually, already tried this, right? So this is on the news, and even some schools complain about this ChatGPT. A lot of students use this platform, right, to do the homework. So instead of students do the homework, right, so computer do the homework. So I also tried this, right, and you can essentially ask the computer everything, right? So I mainly use this to let me see, to ask questions about my research related. I hope that you can also give it a try, right? So I would say right now we are actually at this AlphaGo moment, right? This is a kind of like a second AlphaGo moment. So this is happening almost let me see how many years, maybe 7 years ago, right? And Google actually picked this number 2 human player, right? At that time, right, to compete with AlphaGo. And if you follow the news, right? So you will know that AlphaGo wins the overall game, right? But lose once, right? Lose one game. But if you follow the news, you will know, right? So after that, right? So this AlphaGo actually, have the second generation, third generation, a lot of iterations there, right? And the important thing is the news I read is they challenge the top human being Go players, right? And the AlphaGo actually win 50 times, right? Just 1 month after that game, and no lose at all. Essentially, after this game, right? AlphaGo didn't lose any game, right? Essentially, all right. And right now the situation is all these professional players, they are using the platform, either AlphaGo or some other similar platform, right, to do the training. So essentially nowadays we're getting to the stage that a human being, even these top players, they are trying to learn from AlphaGo or other software. So my feeling for this ChatGPT is a lot of changes, right, will be made for the society. So based on irreversible thermodynamics, right, once we invent this kind of tool, right, so we will have a lot of more these kind of tools actually coming. So no matter you like it or not, right, so this is a reality. We will have so what we are using, probably we can call it overall like the first generation, right, ChatGPT, but we will have the second generation, third generation, right, like that. So our life will be greatly impacted, right? So the ChatGPT team, they need to make a lot of changes, and we also need to make a lot of changes. So what I did is I did a lot of this kind of try for this ChatGPT, and if you see my title here, right? Okay, let me see. Let's try. So their server is so busy, right? Okay, let me see if it will work. Yeah, I have backup plan, but I just want it to run right now. Let me see. Oh no. All right. Let me try something, right? I have the answer, right? I recorded the answer. Where is my desktop? Is here. Okay. All right. Okay. So this is what I tried, right, in the morning, right? So I type in the title of my presentation there, right? Actually, it's gave its response of what possibly I will do, right? So it just predicts, right? So what I may do, right? So as you can tell from here, right? So this is just a one sentence, right? And then you talk about all these things, and you talk about essentially if you actually want to working on these 5 elements, high entropy alloy, what do you need to do, right? Especially if you want to do modeling. So you need have groups working on experiments, and also for the modeling part, you need to do like the first principles calculations, right? And with this kind of a combined approach, you should be able to make contribution on this high entropy alloy field, right? And it is more or less, right, partially correct. It is very close to what I want to talk today, right? Okay. So this slide I can skip. It is about my group. Here, before I talk about my research, I want to talk about what my group actually are working on, right? This is one reason I come to do the seminar, right? Kind of like advertisement. My group mainly working on thermodynamics and kinetics, and we working on different alloys. So today it is about this high entropy alloy, right? We also have a half of the group working on ceramics, right? So like a salt oxide fuel cell, salt oxide electrolyzer cells, oxygen transport membrane, lithium ion battery, right? All those things. Okay, and the approach we use will be the ab initio, molecular dynamics, CAFAT approach, high throughput simulations, and machine learning. So today, essentially, we will talk about the content related to ab initio, high throughput calculations, and machine learning. Okay. All right. Okay. So at first, right? So this chat GPT also introduced a little bit about the high entropy alloy. So here I want to use this very famous diagram, right? To show why we want to work on high entropy alloy, right? So people plot the most popular materials, right? About with their toughness and strength. And in most applications, right? So what we want is the higher the better on both, right? And high entropy alloy. So this is the old diagram, right? So almost 10 years ago. So this is the area, for this probably 200 high entropy alloy discovered at that time. So essentially after that, right, a lot of more high entropy alloy get discovered. And this is what we think, right? So we can expand this oval to here. So if you check, right, this is like this logarithmic scale. So if you do that, right, so no matter toughness and strength will greatly increase. So this shows you comparing with the traditional, metal and alloys, right? High entropy alloy is actually, a very interesting area you can work on. Okay. But to work on the high entropy alloy, we have the challenges here, right? So because high entropy alloy, essentially, if you know its definition, we typically need 4 or 5 elements there, right? And if you talk about the composition, there are a lot of compositions, right? We are talking about. So it is difficult for us to actually develop the high entropy alloy just with this pure trial and error, right? Pure experimental approach. So what do we do, right? Because one group cannot do everything. What we do is we do these high throughput calculations. So this first principle calculations is here, right? ChatGPT actually predict that, right? And then we work on the phase stability, and we need to work on mechanical property, right? So for this high entropy alloy, people discovered they typically only working on some specific compositions, some very special compositions. For us, right, we want to build a database that can that will have the interface for you that no matter which composition you type in, you can get the information. Especially, for example, right here we will demonstrate on this mechanical property prediction. Okay, all right, okay. So we will do 3 parts. Okay, so let's see. Okay, so at first I will talk about this part. This part is about this high throughput CAFAT calculations, right? So it is about this optimized composition screening, and here will be about the first principle calculations that ChatGPT actually predicted. All right, okay. So for this one, for the high entropy alloy, a very important concept is what people have proposed on this VEC rule, right? So VEC is about this valence electron concentrations, right? So essentially you can count how many valence electrons that each element actually has, right? And then you just count those numbers, and that will be the VEC number, right, for each element. So then we can add them together for the high entropy alloy, and people have discovered this kind of a VEC rule. So BCC will be stable and it's a low VEC region. FCC will be stable and it's a high VEC region, and the BCC and the FCC will coexist with each other, right? So we borrow this concept, and we did a lot of simulations, right? So we have figured out a way that we can do several thousand covered calculations. So for the students, actually, taking my thermodynamics course, you will know, right? For the typical computational thermodynamics software, right now, if we follow this traditional way, right? So we do 1 or 2 calculations, right? But for these high throughput calculations, we can do thousands calculations. And we are exploring a way that we can do 1,000,000 calculations now. Okay, so in this work, right, we did like 3,000 calculations. And remember the VC rule, right? So if your VC number is very, very high, FCC should be stable. And this tell you, right, 100%, right, possibility that FCC is stable based on our several thousands calculations. And the BCC, right, in this region, right, you got more than 90% chances the BCC will be stable here, right? So it shows that the VC actually is a very good parameter that we can further investigate high entropy alloy. And here it just shows, right, like the video we created on these several thousands BCC and FCC calculations, right? So the blue dots shows the maximum temperature. This BCC or FCC, they will be stable, and the red dots will be the lowest temperature, right? So FCC or BCC will be stable. So this will give you a range that how wide is the temperature range, right? FCC and BCC will be stable, right? Like that. So with that, then you can figure out what are the good composition for you, right? So then we use this approach, right? So this summarize what we have for these 3,000 compositions, right? And then if you have some BCC high entropy alloy, and if you want it can survive high temperature, right? So this shows you that the one in red shows you that these compositions will survive at a very high temperature, right? And also y-axis is the elemental density. Right? So if you try to select some lightweight alloy, right, and then can survive high temperature, then you work on these two region, right, like that. Okay, so with that, we can do the further screening, right, and tell you about alloys, right? Well, we will have, and we did the screening, and this is what we have there, and we did the final point calculation, right? For this specific composition, we found from the screening, right? So it does show, right? So BCC, right? BCC and B2 actually is stable, and it can survive very high temperature, right? So in this way, we just demonstrate to you that as long as we have a good thermodynamic database, we should be able to use this high throughput CAFAT approach to find the high entropy alloy for you. All right, okay, so phase stability is just one thing, right? And in industry, right, people care about this, of course, right? They also care about like the mechanical property, right? So ideally, they want the alloy actually can satisfy both criteria, right? So here we use the first principle calculations and machine learning, right? And then do the simulation here, right? Okay. Okay, so this shows you how we do the simulation, right? So at first we did the high throughput DFT calculations, right, for pure elements, binary, ternary, quaternary systems, and then we can combine them together, and we can do the machine learning. We will have the phase stability and also the mechanical property there, right? So specifically things like bulk modulars, shear modulars, and other elastic properties that will give you a pretty good idea of the mechanical properties, right? Okay, so I think so for example, right? So this shows you, right, our calculations on the bulk modulars for these 10 ternary systems, and also the 5 quaternary systems, right? For the quinary system, we can do that too, right? Just like it is not easy for us to view it, right? Because it's a high dimensional diagram. Okay, so for quaternary, this is a zoom in, right, to show how the bulk modulars, right, actually looks like. We did the similar things on the shear modulars, right? So the good thing is we have the whole map, right, of everything, right? Okay, all right, and we actually compare with the experimental data, right? So the red one is from experiments, and then the black one will from our calculation. So you can see, right, we have a very good match with experimental data, right? All right, okay. So, all right, okay. So those are like our DFT calculation results, right? So we use that, and then we did the machine learning, right? Okay, and with that we built the database. So you will have a good idea of phase stability and also the mechanical property, right? For FCC, PCC, for this 5-element system, right? So this is how we do the machine learning, right? Okay, so this is to tune the parameter, and this is we did the machine learning step by step. Okay, so then you can see, right? So this is the DFT calculated results, and this is the machine learning predicted results, right? So you can see we have a very good match, right? Because this dashed line is the ideal case, right? So, and our data has a very good match with each other, and this shows when we do the machine learning step by step, right? 1, 2, 3, 4, and then this binary system actually didn't change. So we follow this Kappa approach, right? So we fix the binary and then ternary and then quaternary, and then we can predict the high order systems, right? Okay. And then with that, right? So we can plot. This is about 300,000 points we have for this 5-element system, right? So this is the top one is for FCC, bottom one is for PCC, right? And then in this whole composition space, right? What we found is the alloy actually match this entropy alloy definition will be in here, right? Okay, like that. So the first one will be the phase stability, right? So the lower, the better, okay? And then the second one is the bulk modulars, right? And then the third one will be the shear modulars. So you will see, right? So for the entropy alloy, right? So the region it will we will have, right? For the bulk modulars of the shear modulars. Similarly, we have for the PCC as well. And then with that, we can do the screening, right? So based on the bulk modulars, shear modulars, and other, elastic constants we can get. So then we can figure out, we can do the screening, right, of the mechanical property, and then we figured out the composition of aluminum, iron, cobalt, chromium, nickel. So with those, you can get the entropy alloy candidates, right? Like the composition, right? And then before you actually make the alloy, you will know roughly, right? Like how the mechanical property will look like. All right. Okay, and this is how the software, right? This is a software interface, and we have that in this GitHub there, right? So you can go ahead and download that. So of course, right? So there we have this demo version. So you can do the point calculations, right? For any composition in this 5-element system, we can give you the the elastic property. So that will give you an idea of the mechanical property. And then if you know your composition range, right? So this can do thousands, or even tens of thousands calculations for you, right? Like that. And with that, you can do the screening by yourself, right? Okay. So if you have interest, just go ahead, check here, for the details. All right. Okay. So we are not done yet, right? So we know the phase stability, we know the mechanical property. However, right? So this is the mechanical property prediction from at 0K, right? So for the high entropy alloy, in many cases, we want to use at elevated temperature. So we want to know how the mechanical property actually will change with temperature, right? So this is the third part, okay? And this part is very expensive, right? So that's why we don't want to, for any arbitrary composition, we do these calculations, right? So with this database, if you find some composition has a very good mechanical property and 0K, right? So then just tell us, we can give you this alloy when it increased temperature, what will happen, right? So for example, right? So these are like some preliminary results we have, right? So for the Bach modulars, shear modulars, Young's modulars, right? In comparison with experimental data, right? So this is with temperature. So with this, right, before you actually make the alloy, you roughly have an idea, right? How your alloy actually will survive at high temperature, right? Okay, like that. All right, okay. So that's very briefly, right, about what we have achieved. Okay, so with this, essentially, we have used this high throughput carbon approach to quickly identify, right, high entropy alloy. And we have used this DFT and machine learning, right, to figure out the elastic properties and also the entropy formation, right? And we have figured out these elevated temperature properties, right? In the future, actually, we want to establish a very large mechanical property, right? BCC, FCC, B2, L12, right? So when I say very large, it means one is, right now we only have 5 elements, right? So if you have more elements, right? So we want to include that. And another thing is, besides this BCC, FCC, I demonstrated, right? So for B2, L12, and some other, phases, we want to include it, right? So that's pretty much, what we have done. At the end, right? So I also want to show you, what I did, right? So I put this again, right, in this chat GPT, right, to see, how ChatGPT actually summarize. All right. Okay. So this is the response I got from the ChatGPT, right? So at first, right, it is that it is very important, right, to consider the elevated temperature property, right? Same as what we think. And it also said that our database is valuable resources, right? It provides comprehensive understanding of the property, right? And it also said that this is a good direction, right? So expand, BCC, FCC, P2, A12, right? So like that. Yeah. Okay. So that's pretty much what I want to share today. So the main thing, not just my research, right? The main thing is the new changes, actually coming. So don't just expect you to same old, and you get different, results, right? So the changes are already here. So you have to make some changes. Don't just follow the traditional way to design, to work on materials, right? So I believe even with the current ChatGPT, don't limit yourself, right? Don't just use ChatGPT to do the homework, right? But work on your research in a good way, right? In a good way. That's very important. All right. Okay. So and end, right? Always end like this, right? Happy thermodynamics, because that's what my group actually is working on. All right. That's what I have. Thank you.
Okay, we now open up the floor for questions for both people online and in the room. Feel free to ask questions. Let's see how to. Yes.
I was thinking you could explain the valence electron concentration. How do you calculate that for like just a single atom? Is that a simple calculation?
No. The VEC depends on your composition. So for each element, you have your specific VEC. For example, aluminum, it is 3.
Oh, that's all.
Yeah. And then based on your composition, you calculate, right? Your VEC.
So it's just basically the valence.
Yeah. Exactly. So in the past, right? So at first, the people got excited. Okay, so there is a new concept, and then a lot of other people argue. So do you have physical meeting there or not? Right. So then people try to prove again and again, right? So we use our own way to prove that, yeah, actually, right? So based on BCC and FCC, so you will see with thousands calculations, it shows you the possibility that the region, the FCC and BCC, they are stable, right? So it has a pretty good match with this BC, rule, right? So it is not a perfect rule. My student Zhong actually proposed a modified VC rule. Yeah.
Okay. Any more questions?
Yeah.
What other properties are you interested in predicting with this model? Are you so obviously you showed the strength and fracture toughness at the beginning. Do you think that it would be possible for your model to
yes,
for those in the future?
Yeah. So it is not that difficult. It's just like when we originally work on this, we didn't consider that. We plan in the next version of the plan, we plan to include that. Yeah. Yeah.
So I had a question about the plot you showed with the different phases and their stability ranges.
Yes.
So the simple question, I guess, is what are the two phases and how different are they?
Hold on. How do you probably need to. You need to find the mouse first, right?
Right in the middle.
Okay. Yeah. Okay. All right. Yeah, because the time I skip a lot of details there. You are talking about this one, or you talk about yeah, here, right? Okay. Yeah. So exactly, right? So the first thing I introduced is the BC rule, right? And the second thing is, as long as we do this covered approach, right? The first thing is how reliable is the thermodynamic database, because garbage in, garbage out, right? So then what we did is we did some calculations, right? Just purely based on the database, and then we did the literature search on the experimental data, right? And essentially, at first, right, based on the predictions. So here, this is FCC, right, region, and this is BCC B2 region. So B2 is kind of like a ordered BCC phase, right? So
that was the first one.
Yeah, the whole region here in the current work, right? We use this broad definition, call this like the BCC, right? The whole thing. And then here we have FCC and the BCC mixture.
Is the phase boundary in the pink area an order disorder transition?
Yeah, so here actually a lot of things happens. I will show you, but before I show you that, I want to show you the how these results in comparison with the experiment data, right? So liquid solid line has a pretty good match, right? And then this FCC and then BCC boundary, right, has a pretty good match, right? And also we have additional, this kind of verifications on that. So overall, this database is okay to do the calculations. And here, this is not just a simple one. So let me show you. Let me see. Right. Okay. So here, this is as I say, right. So this is a broad definition of BCC, right? So it will include the disordered BCC and also the ordered one, right? So as you can see from here, we will have more than more than one B2 phase actually forming there, right? So we have right BCC, B21, B22, right, like that. Yeah. So but overall, you will see if you broadly say this is a BCC, then essentially, right, you have everything just BCC.
Good.
Yeah.
This is exactly where my second question starts.
Yes.
With this chart.
Yeah.
How different are those spaces? And would you expect something like boundaries moving around
does the volume fractions change like a sheet memory alloy, or is it that they're just local concentration variations with roughly the same mechanical properties? What does this look like?
Yeah, I would say because a lot of this type of work have been done. So because these two phases are actually so close to each other. So if you have a single phase and then decompose kind of like this spinodal, decomposition. So mechanically, right? They can be good neighbors with each other. So for example, in like this superalloy, and then people actually use this kind of concept, right? So for example, FCC L1, 2, right? So the and together, and then can further strengthening the alloy. So, but that is like this microstructure level, right? So, yeah.
Okay. So to summarize, maybe
Mhm.
these two are very similar.
Yeah.
In terms of lattice spacing and so on, it may strengthen like a gamma prime.
Yeah,
or
yeah,
it may not.
yeah.
The boundaries may be mobile. It may be just a chemical ordering, and someday someone will know. Is that?
Yeah, so one group cannot do everything, right?
Sure.
So as material design, we need collaborate with a lot of groups. So for example, here we can predict some good compositions and figure out roughly how the property will change with temperature. And then we need the people actually do the experiments, actually plan to purchase a furnace actually to make this alloy, right? And so make some small buttons there, and then check the microstructure to see how this works. Yeah.
Exciting. Thank you.
Yeah. Sure. Yeah.
Okay, more questions? Okay, so we're good. Thank you so much again for the
Sure.
great
Okay.
presentation.
All right. Okay.
And we
Thank
end
you,
the
everyone.
seminars here. Thanks to everyone.
That's full question today.
Yeah.
All right, so, yeah, okay. Just close, right? Close here. All right, okay.